So Dr. Jamaz was explaining us about cyclotron and what we need for doing some radiopharmaceuticals, but as he already mentioned, the most important is for you, for clinicians, to decide what you want to do with that technology. Chemists can do many compounds, many isotopes, but it really needs to be driven by clinical demand. This is very old chart, what you see here. It was prepared more than 10 years ago. And you see that the most used, most important radiopharmaceutical is fluorodeoxyglucose, because it is so good in detecting cancers. And if someone would make a trouble to prepare the same chart for the last year, for example, you will see that the gap between FDG and other tracers will be even more. So the major radiopharmaceutical we want to make by the cyclotron would be FDG. So at least this radiopharmaceutical should be there with the cyclotron when you buy it. So there are different types of cyclotron facilities. It can be very simple, from just making FDG for your local hospital up to very complicated large energy cyclotron facilities with a lot of isotopes. For you to help, there are already materials published by International Atomic Agency, and you can download them from online, and you can consult. They are quite good explaining on high level what are the needs for cyclotron facility. So the major point is that your facility which you are building must fit to what you want to do. If you don't need to distribute your radiopharmaceuticals all around the region, don't go for complicated solutions. There are simple solutions. And actually everything has to be carefully planned from the very beginning. So as Dr. Jamaz already said, there should be some future thinking as well, because all mistakes you do in the beginning, they have some cost implications. So the simplest facility would be small center producing just FDG, maybe some couple more tracers just for local hospital. That's already expensive, but not exaggerated. You don't need that many people. On the other extreme, there would be a larger machine which can do many different isotopes, can do a lot of research radiopharmaceuticals. That will of course cost a lot more money. It will be need in many more experienced radiochemists to run it. So the problems will be at the other level. So you really need to decide what you want from that facility, and it has to be driven by clinical demand. Typical timeline for building cyclotron facility from when you decide, okay, I want it, I have the site, to really starting real productions for clinics normally is about 3 years. When it is public entity, it can double the time, 6 years. And just to draw your attention that validation activities, which has nothing to do with equipment, it's just how you use that equipment, can be quite an expensive exercise. So you already saw these 3 letters, GMP. What do they mean? What is this GMP? Good manufacturing practice. So actually it is the set of rules which was created for big pharma industries to assure that the products they make, the drugs, they are safe for patients. And the same rules apply for us. We don't do large batches of pharmaceuticals, but still we inject into patients, and we need to make sure that our product is safe and that it does what it says on the label, that FDG goes to the tumor and you can do diagnostics. So this is all about making your production reliable, consistent, and that the product we give into the hands of the doctors is always safe to inject. And the reasons why do you need to bother with all these rules which were created for big large pharma industries is that patient has no chance to detect was it good, was it wrong. So we have the responsibility to assure that every time we make our radiopharmaceutical, it's that what we say. And when we test, we don't test every single vial. We test only small portion of the batch we produce. So you cannot test every single vial. That's the reason for GMP. It is just a set of rules to assure that when you do your production, it's always the same. So very often people mix up what GMP. So we just control the sterile environment in our production, and this is GMP. Of course, you need to do it. You need to do all the tests to assure that the laboratory you are making your radiopharmaceuticals is clean. There are a lot of tests to do. This is weekly tests we do in our labs in Cambridge. But it's not all. GMP is much more. It's much more. So there are regulations on GMP, there are guidelines, there is an International Commission for Harmonization of GMP rules, there are American rules, European rules, but if you don't want to choose, to go with the States or to go with Europe, there is also the International World Health Organization GMP guidelines, which you can download from internet, which you can use, and they are quite comprehensive. And actually they are the same as US or European. And basically all these guidelines, they treat about premises, how you build your facility, about the paperwork, which is important part of GMP, about processes, how you set them up, people, which are a key component in GMP, and the products themselves. So how to arrive from the plot, which you have decided this is good for your cyclotron facility, to really facility producing radiopharmaceuticals. By the way, this is just the corner in between reception and the main hospital building in Geneva. That's where the cyclotron was put, so you don't need much space for that if you plan well. So you start with analyzing your process. So, and actually you need to go carefully in looking into each single component of the process. Some part you can rely on experience from the industry, but there will be some point where the responsibility comes to you, to the manufacturer, to people who use the equipment. So the people are very important, and it is better to start training people from the very beginning when you have decided that, okay, we go for cyclotron project. Then you start identifying those people and send them for training. Experience is a key here. And probably cyclotron installation in itself is just the simplest part of the whole story, because the technologies are there, good engineers know how to install cyclotrons. If you look, if you decide what you need from that facility, you should start looking into the final vial. You should start looking from the product itself, what type of products we are making, what we need for that. So everything starts from the final vial. And this is the process which we use to produce FDG. So everything starts from the cyclotron. You transfer isotope produced by the cyclotron into the hot chemistry laboratory. The automated modules, synthesizers, do quite a complex chemistry inside. At the end you have a vial which you then just need to sterile filter and check, and it's injectable. So if you go for a large batch to distribute, let's say for 10 different scanners, you would need about 4 hours from the start of the irradiation to the end to produce FDG. And the GMP rules, they advise you how to build those facilities which will be fit for the purpose. So they're purpose built, and all the processes have to be carefully planned. Radioprotection is not the part of GMP regulations, but it shouldn't be overseen. There are some risks connected to working with volatile activities, and radioprotection is all about just managing those risks. You can ask from the manufacturer of the cyclotron to provide you with the worst case scenarios. And there are solutions for all those risks. Cyclotron technologies now are very safe. Most of those 800 cyclotrons installed in the world, they're installed in a hospital environment, and they work every day, and they're quite safe. There are solutions for everything, starting from the cyclotron bunker, which is nowadays made like a closed, sealed compartment. This is the door for the cyclotron in Geneva, so the doors are quite heavy. But they really do the job. They provide a good protection for people working there and for the environment. There are solutions to trap all those risks of contaminated air. And of course, you need to monitor the air. There are specialized companies who know how to monitor air contamination with quite a high precision. So all this you should consider. And when you are planning the facility, what is important to plan your ventilation systems. And here we come to the conflict between GMP rules and radioprotection rules. To protect people and environment, we need negative pressure in the rooms. To protect product, we need positive pressure. So this has to be carefully considered. There are experts who deal with ventilation, and that can be addressed from the very beginning and must be addressed from the very beginning. But what is important that whatever you put on paper then has to be measured in real life. There must be everywhere the device which will measure the pressure in those rooms. And you see that what can happen sometimes when the constructors are not very diligent. So we have spent quite a bit of time finding those things and making everything good so that we could achieve what we have planned in the reality. So in PET, what is important to work is in aseptic conditions, because we cannot sterilize by heat our products. They are very thermally labile. And for this you need to have special pieces of equipment which are isolators, which will be clean room isolators with class A. And here on this slide you see the minimum GMP compliant laboratory. So your laboratory where you put your hot cells should be class D. Inside the hot cells where you put your automatic synthesizers should be class C. And then the final place where you put your product into the sterile vial which goes to the patient should be in sterile environment, class A. And this works, and there are processes which are registered with this kind of approach. So aseptic processing is there to minimize the risk of contaminating product with bacteria from external environment. So there are laminar flow hoods to use, there are all the procedures to use. You just make sure that at every step of the process everything is clean and not a single bacteria can get into the final vial. Important part of the production is quality controls. This is just to show what we test before we release the product. There is one test which we cannot finish before release, which is sterility. It takes 2 weeks for bacteria to grow and make sure that the product is sterile. And this is the reason for all those validations, extensive validations that we need to do, because when we give our product, we are not sure what's inside. We cannot say it is sterile. We just can assure with all our validations that every time we do it, it is sterile. It looks very complicated, but in fact, with good thinking, with good organization, with proper instruments, all those parameters you have seen, you can do in 30 minutes. You can obtain all the necessary parameters to release your product. So it can be done before actually the product is given to the doctor. A couple words about sterility and GMP compliance. So there are simple ways to assure sterility. You just do terminal sterilization. You autoclave your product. And many SPECT products, they go this way, and the life is easier. You just put autoclave and it's okay. But for PET, unfortunately, most of our pharmaceuticals are not stable, you cannot heat them, and you need to work in aseptic manufacture. So then sterility testing and especially extensive validations become really a key here. And if normally for sterility testing you would need also this certified laboratory which you outsource your sterility test, but if this laboratory is not available in your case, you should plan for sterility testing laboratory, which is also some additional equipment, additional sterile laminar flow hoods, and additional expertise, because you need special people trained to do sterility testing. So we must do a lot of validations, which so it starts from the very beginning, from designing the facility, from equipment validation. You need to validate that your rooms are sterile, and you need to show it with real tests. So for some part of these validations, there are specialized companies who know how to deal with ventilation, how to validate clean rooms, but some part of the tests lie on the end user, because you cannot invite someone to validate your process. It's your process, your product, and you bear the final responsibility for that. So there is a lot of things to plan, and yeah, that's how it goes. It all starts from your user requirements. What you want to do, what you want to achieve with this product, what you want to achieve with this equipment. Then there is an important phase, design qualification, where you check that what you wanted is really put into the design, and then you start testing it step by step, that installation is okay, that the equipment which was installed works properly, and finally that the whole process works properly. There is a lot of paperwork related with these validations. There are guidelines how to deal with this paperwork, and important is that you start from the very beginning. Principle of GMP is write what you do what you write. So you start writing from the very beginning, and for this you need, of course, people who know how to deal with all this. And it looks complicated, but if you start looking at every single process, so there will be always someone who knows what's going on there, and who need to start writing those procedures, those tests. So at the end, it can look something like that. This is just a simple FDG producing facility with all the GMP papers, there. For more complicated processes, it will be more, but this is the must. So write what you do what you write. That's the principle. And if it is not written, it doesn't exist for GMP inspectors. So that's the first thing, the quality assurance system. That's how you assure that whatever you are doing is correct. So just briefly, what is all those abbreviations? Design qualification is meant just to make sure that what you requested is put there in design. And there must be, at some point, official document saying that this design corresponds to your requirements. Then only the manufacturer can go and start producing it. Installation qualification is when everything is delivered to you, put on place. You just check that what was in design is now really standing in your laboratory. And sometimes there are quite a lot of surprises. So there is one step in between, which is called factory acceptance test. That's where you can pick up all those points which will be too late to correct later when the equipment is installed in your lab. Operational qualification is just to make sure that all those buttons, knobs, and things in the equipment, they function correctly. So there are protocols. You clearly define what you want to achieve with pushing this button, and there will be a result of that test. That yes, the button starts the ventilation. That parameters are okay. Final test is performance qualification. This is the test to assure that the whole process provides you reliably, consistently the good product, and that's where the major cost of validation and
doctor,
effort, and that's where.
You still have
I'm coming to the end.
One more minute.
Couple more slides. And people are very important, and you should start training people from the very beginning. You can have the number of staff must be adequate. So for small FDG production facility, it can be as small as this. 4 people is enough. But for some bigger operation, you need more people. And this is example of the organization chart for cyclotron facility producing for other centers and not only FDG. Reliability of production is a very important thing which must be addressed from the very outset of the planning, and the key here is again training of your staff and regular maintenance. So I'm finished. So just to conclude that GMP is important part of radiopharmaceutical production. It is there. You must start it from the very beginning, but it's easy when the system is on place. So thank you very much.